And Colin DeGraff had asked Andrei Kravtsev and me to lead the final discussion. And Andrei and I agreed on, actually Andrei proposed this set of questions. And we're going to use the same method that was used yesterday afternoon. So I'll stay on this side and give the microphone to people on this side, and Andrei, I think, will stay over on that side. And why don't you start, Andrei, with the first question?
Do clumps exist? Go. In simulations.
Yeah, there's no question, I think, that clumps exist in high redshift galaxies. And stars. They see stars, they don't see gas.
Wait.
The stellar masses that Yiching, Guo, and Stein-Woots and the other authors are seeing are in the 10 to the 8 and up range, and the sizes are half a kiloparsec to a kiloparsec. I mean, this is just telling.
I just remember a paper from Stein that was showing that the distribution of the stellar mass was very smooth compared to the distribution of the light. Right, the stars are very smooth; they're not clumpy.
Yeah, so these are star-forming regions, and so the way Yiching Guo does it is he's only looking at rest frame UV light to measure the clumps, and I don't think there's really any dispute that there are clumps.
I guess the issue is how much mass is actually in stars.
Well, so Yiching's scheme requires that 8%, that at least 8% of the UV light is in a given clump. Otherwise, and it has to be off-center to be called a clump. The total amount of star formation associated with the clumps is 15% or 20% or something like that in typical examples, according to the published paper. So it's not a huge fraction of the star formation, but the question, which I think is still worthy of discussion, is it true that simulations that don't produce clumpy galaxies are suspect? That this should be an important criterion for deciding how much feedback or other things are put in the simulation. Avishai and I think Daniel Severino think that it is an important criterion. Lucio Myers, the first author of a paper that came out, I think, a month ago on the archive, that made the same argument. They ran several simulations, and in particular, they had superbubble feedback, which never produced significant numbers of clumps, and they argued that that means that that's bad. That's not a correct feedback prescription. But other people may have different views, and another thing that has not been done well is to correct for dust. So Sandro Tekela told me that he thinks that the problem with dust is not that the clumps are dusty, it's that when you correct the background disk for dust, the disk will get brighter and the clumps contrast will be less. And the problem is nobody's done a good job of correcting for dust globally, and so that's another issue. But I don't want to take all, I mean, if people aren't interested in discussing this,
yeah,
then...
The problem with clumps is that once they're created, if they're created for good or wrong reasons, there could be also problems with their dispersal, because if nature disperses them for a process that's not modeled, then they can really change the whole galaxy evolution. We see this in isolated disk simulation. If you don't do feedback immediately, the disk just creates clumps and they're like very long-lived and it's very difficult to disrupt.
Incidentally, Yiching is here, so I shouldn't be summarizing the data the way he can. Also, I just want to remind you that I showed Yiching's plots yesterday, or rather this morning, and what Yiching shows is that there is this strong radial dependence in age or color, especially in the lower mass galaxies at all redshifts from 3 down. It's not so strong in the higher mass systems.
The question maybe is how do we tell when clumps in simulations are real? Because there are many ways of making them for wrong reasons, either or they could survive for too long, for example. So how do we know when the clumps are real and when they're not real?
Well, I didn't mean to answer that question specifically. I think, yeah, I know. I've been studying clumps for a long time. I think just to kind of summarize what Joel said and what I said earlier today after his talk, I don't want to state too strong an opinion over what I think in the real universe, how long clumps should live, how much mass they should have, all which is weird considering I've written at least 2 papers about that. But the only point I really want to make is that we have to start using clumps and similar phenomenon as diagnostic tools to calibrate our the feedback that we have. I think there's been far too much emphasis put on only matching the stellar to halo mass relation as a sign of saying, oh, my feedback is good, my feedback is bad. The clumps and the other morphological structure in the galaxies, which are extremely sensitive to the details of the feedback, should be used as the key diagnostics, in my view, going forward when we have more and more different models of feedback, each claiming to be much more realistic than the other ones. We really should be focusing on these issues that are very sensitive to how feedback is implemented to try and calibrate is feedback good or not. And this requires very detailed observations of, for example, clumps together with simulations. And yeah, so.
So comment from Mike.
Yeah, so Nir sort of got that point at the end that I was going to say, which is that I think, I mean, what Andre was saying, that if you want to use something as a diagnostic for simulations, you have to understand it enough to be able to tell when your simulation is producing something that's actually that or something that's artificial, which in the case of clumps I think is very possible that simulations could cause something that looks clumpy that's actually clumpy for the wrong reasons. So I think until we understand very well, you know, the time, how long clumps should survive, and, you know, more details about them from observations, and maybe that those details already exist. I don't know enough about that to decide, but I think you do need to get the observations to a certain point of maturity before you use it as a diagnostic for simulations, especially when it comes to the detailed structure of galaxies, which again, lots of things can happen artificially that aren't good, that you can convince yourself are actually good.
So, yeah, so to move on, another thing that kind of worries me is when I hear compaction, I'm really scared because for 20 plus years, people have been fighting to avoid compaction. I showed you one example where, you know, if you don't do feedback is weak, things compact. And then they never uncompact.
The old overcooling problem.
Yeah, so the same kind of issues, I wonder, you know, when can we tell that compaction is the sign of weak feedback and when it's real?
Basically, it's because of the gas fraction. If you find a compact galaxy that is gas rich, it's not because of overcooling. Yeah.
I think that if you have stronger feedback, you don't prevent the compaction, which comes from a merger or another outside effect that drives in gas. It's going to speed up the quenching after the compaction. And in one simulation I showed you with a very strong feedback, including AGN feedback by Johan Dubois. This is what happened. Okay, there was nice compaction that immediately shut down everything because the feedback was much stronger. If the feedback is not so strong, you have to rely on gas consumption to star formation after the compaction.
I wonder, so my question was about what diagnostic can we use when it's weak feedback with a real effect? So how can we tell? How can you tell compaction that's real from the one that is due to weak feedback?
Well, one possibility is...
Oh, so the speed.
This is a drastic effect.
But also, the characteristic feature in the simulations I thought was nicely summarized by Sandro Tekela as a phenomenon of outside-in quenching followed by inside-out quenching, just quoting from Tekela's paper. So the idea is that the gas is drained out from the region around the center, leading to the center being bright and the outside not so bright. But then the center forms a lot of stars quickly and uses up the gas or dries it out, possibly with the help of an AGN, and that leads to the inside-out quenching. So that's the characteristic thing that's seen in the simulations, and at least the Barrow paper suggests that that's consistent, and Sandra's work also and other work, with what we see. It's not a completely convincing story because the problem is that in observations we only get snapshots. And the way you deduce that these things are actually happening is by comparing different redshift intervals, and of course you're looking at different galaxies. So it's not a direct observation argument, it's an inference. On the other hand, when you see these extremely dense, very rapidly star-forming regions in the ALMA data, it's hard to see how else they could have formed by some process like compaction. But maybe there is some other way. I don't know. That looked like sort of
so
smoking gun
I don't worry about real universe doing it right. I worry about us in simulation. I'm pretty sure the universe knows how to do compact.
No, but then the simulations. So the challenge to the simulators with high enough resolution is to actually reproduce what the ALMA data is starting to tell us, and will be telling us a lot more.
But this seems like a very complicated diagnostic. I mean, so I wonder, how can we tell from other, like, simpler things on the galaxy? So how do I know that my galaxy underwent the correct compaction stage rather than, my feedback just is wrong?
Yeah, so there's one regime where we know compaction doesn't happen, and that's in, say, 10 to the 11th solar mass halos, which make bulgeless galaxies. And so that's a good place to test a code, because if it makes lots of bulge-dominated galaxies, then you know there's a problem.
Compaction within the trigger. You need something to...
I just said one diagnostic is of simulation. If you see outflows coming right after this compaction, instead of that's one of the ways to see that the feedback is somehow regulating the gas fraction in the galaxy. If you have an overcooling problem, again, you can have a compaction event, but all the stars, or the gas goes to the stars instead of being removed away.
If it was only feedback, what you're talking about is an overcooling situation. And this should probably take continuously from very early times to late times, right? You simply have the gas fall in and make stars and get stuck there if you have no feedback in the extreme case. This will not look like a sudden compaction event. The compaction we see is, the galaxy lives happily on the main sequence, and it has normal and self-regulated star formation, and then one day it decides to compactify because something happened, like a merger or colliding streams or something.
But I showed in my talk example where the same halo was simulated, and in one simulation it was happily following the same evolution, and then went crazy and became a low diffuse galaxy. And I'm pretty sure that's wrong, because if I change feedback, it changes. But then, it exhibited this behavior that it was doing something happily living on the Bernoulli relation and then went off it. And in this case, I know that can't be right. This is too sensitive to assumptions. Right. So I think what I heard, this was what Aaron said was very, I think, productive and constructive, because the regimes where your code should not be producing compact galaxies. And when we had the problem with compactification due to numerical reasons, it was actually happening across the whole mass range. So,
Right.
Yeah.
So I think
New simulation with stronger feedback, and hopefully we'll be able to test the appearance of compaction in them soon.
so. Actually, the first three topics, the two that we've talked about, clumps and compaction, we should join with the point that Aaron made. We also want to get the disks right, and we don't want the disk to be too thick, and we don't want the disk to form bulges that are too big, because there's a tremendous amount of data, and small disks are either bulge-free or only have pseudo-bulges. So that's certainly another strong constraint. Anyone want to comment on the issue of disks, or any combination of these three criteria, or are there any other criteria that we should be thinking about?
Yeah, this is not something that was discussed here, but we saw a lot of movies where you see these outflows destroying galaxies at high reaches, And stars are forming out of the gas that's been pushed around violently, right? And the it's not really advertised, but my impression that in most simulations, the old stars are in a pretty thick disk. So I just wonder whether people have opinions or whether we have a problem or not with these violent feedback models. No opinion or no problem? Oh, touchy topic. So, yeah. Do you guys look at it in Nihao?
Yeah, we have looked at it, but the thing is we don't have the force resolution to resolve
that's a problem.
The disk, so...
But if we don't have time force resolution to resolve the disk. I mean,
the scale height.
Yeah, but yeah, do we have force resolution to do anything?
It's a good question.
Just a comment, in Daniel simulations, which have pretty good force resolution, we often see new stars that aren't in any kind of thin disk at redshifts of 2. Rather, there'll be some material falling in, and they're shocking, and you actually make a bunch of stars well above the midplane. So if that's what really happens in the universe, and it certainly produces mock KMOS observations that look just like the real ones, which are often interpreted not as shear or merging, but as rotation. We have to be very careful at interpreting the data, because what can happen in these high redshift galaxies can be pretty complicated. They're nothing at all like low redshift thin disks.
All data has to be confirmed by theory.
Okay, any other comments on disks?
Speaking of tests for feedback recipes, I think methodicity is a very strong test, simply because the source of metals and the energy source for the feedback is coming from same thing.
For the lower mass galaxies.
For the lower mass systems. Yeah. So I haven't seen much discussion, at least in this workshop. I think it should be a very interesting topic.
Yeah, but the mass metallicity relation for dwarfs is a very strong, very robust set of data.
Yeah.
And I mean, it's as far as I know, there are almost no outliers. It's really a clean, robust result observationally, and so that's another very strong test for theory.
Yeah, and for the field and also for the local environment.
Right. So, and it's going to require a lot of high-resolution simulations. So we move on to what effects do unresolved fluid dynamic processes have on our modeling of outflows in galaxy formation simulations? Do you have to have the ability to do 1 trillion cells the way Brandt described in order to do this right? Is Brandt still here?
No, he left.
Okay,
but I was impressed that in Nihao, there was a talk earlier this week that actually simulations reproduce H1 column densities, because I know that from our work and from other people's work that it's very difficult. So I was wondering whether you guys have insight about what as absorbers. How does H1 gas survive in a halo in massive galaxies? So typically we get, the same violent feedback just gets hot gas, but Brandt was showing that it's very difficult to get the cold gas out, but even if you have huge resolution, but even at low resolution it seems to disappear. But somehow it doesn't happen in neurons.
So I also quickly showed the maps of the H1, and they're much more clumpy than the oxygen 6 that I was showing, for example. The oxygen 6 is very much distributed. And I haven't checked it in detail, but I think a lot of it is actually still inflowing material. So we get some of the H1 because it's cold inflowing stuff. There's a certain amount of cold outflowing, or stuff that's come from the galaxy, but I think partially it's due to the inflowing stuff. Yeah. So that's our covering fractions of H1 for at high redshift match much better than at low redshift. So definitely, I think So we get the covering fractions at low redshift for inside our VIR, but not further. So there's also observational covering fractions for 2 VIR radii, and we're too low for that, definitely. So we match a lot, but not everything.
I wonder, I know that people in the fire calibration argue that there should not be outflows at low redshifts in like Milky Way sized galaxies. In fact, there were papers written on this. Below redshift 0, because the gas fractions get low, it's very difficult to get cold gas out. I don't know if anyone from fire calibration wants to comment. That's also what we see in our simulations, but that contradicts the presence, ubiquitous presence of cold gas in halos, or warm gas.
So the data that's available is on many different species, not just neutral hydrogen,
right,
but also low ion metal lines and high ionization metal lines. You mentioned oxygen 6, but from quasar absorption line data, we know locally that galaxies have very extended low ionization silicon 2, aluminum 2, things like that, that fill a significant part of the halo, and higher ionization like carbon 4 that fill probably the whole halo. And we also know from the COS Halos project that oxygen 5 is a very good diagnostic of whether the galaxy is star forming or not. You see it if it's star forming, you don't see it if it's not. So this is another strong constraint on feedback. The feedback has to be such that it doesn't overheat the gas, but it does drive enough of the metals out and produce the right ionization states to correspond to what we see. And this has not been sufficiently exploited as a constraint on theory, but it should be.
Well, people did a number of comparisons. Pretty much every major group did a comparison, but with absorption data. But in most cases, you fail because there's not enough warm gas in the halo. And when there is, you see that it's pretty strong outflow. So you are sort of required in that picture, if it's outflow material, you're required to constantly drive outflows to redshift 0 because this stuff is even at low redshift.
So for Daniel's generation 1 simulations, these are more massive simulations with 35 to 70 parsec resolution. The paper that Michele Fumagalli led showed that we actually had a pretty good agreement with the H1 covering factor, but horrible disagreement with all the low ion states. We drastically underproduced them by 1 or 2 orders of magnitude. So
that's metallicity effect, yeah.
It's a tough constraint. This is not going to be trivial. Okay, should we move on to gravitational instability versus self-shielding settling?
And also people should feel free to bring up burning issue that needs to be resolved before we separate. That's your last chance.
Yeah, so this is, I guess it's mostly a question for you two.
For you two who?
So, Andre and Vadim.
Oh, okay.
So we've seen that if you have a low star formation threshold, say less than 0.1 per centimeter cube, you tend to, the dark matter halos and dwarfs just stay NFW. But if you have a higher threshold, 5, 10, 100, then you get bursty star formation and you can drive halo expansion. So what do you or other people think is more likely to be the right answer?
You first.
And how can we test this?
Well, I think, so since Governata et al., I think the picture that emerges, and Phil has argued the same, and the results that I showed seem to indicate exactly the same thing, that more compact distribution of star formation, not the amount of star formation, not even amount per kiloparsec squared, but how it's distributed. The more compact distribution, the more efficient a given feedback model is. So for a given feedback model, if you change the distribution of stars, it means that star formation matters, right? So what we get in our model is something in between what Phil gets, like very high threshold essentially, and if you use like H2 or something of order 5 or 10 centimeters. So I would think that if you use a threshold of 5 or 10, which should be similar to what molecular hydrogen for solar metallicity gives you, that would be too distributed. But at the same time, I'm puzzled by the result that I saw in Phil's plot that it doesn't matter what the threshold is. So that I don't understand why it doesn't matter. Because I would think that the higher threshold would make things more compact.
But a threshold of 0.01?
That's wrong.
Okay.
Threshold for star formation 0.01?
Yeah, the Eagle code is It varies metallicity dependent, but it 0.1 to 0.01.
No, but that's a different regime, right? So in Eagle simulation, they're essentially treating galaxy as like a cube, like a big.
Your resolution's only a kiloparsec.
I think so. That's partly what I meant. I don't mean to say that it's wrong. My comment that it's wrong because if it was a zoom-in simulation, and I think stars do not form at 0.01, so a CC, right? Okay, so then I don't know. I think, yeah. I mean, 0.01 is a hot medium, coronal gas, right? So stars do not form out of coronal gas. If you're at low resolution, maybe to form a galaxy, you need to come up with a model that works at low density. And partly, I subscribe to that. Your prescription has to be applicable to the scale you're working at. And if that prescription works at that scale, that's fine. If you develop something sensible, but it has to be based on some physical model. That's my opinion. In zoom-in simulations where you reach 100 parsec scales, that's just not acceptable, I think, because we know that stars are not forming holes in coronal gas.
Well, I just want to add a comment to that. So yeah, I mean, the density threshold should be resolution dependent, and it should be roughly predictably resolution dependent because you can estimate, given your spatial resolution, the sort of density regime where, beyond which you no longer effectively are resolving the gas, right? So, for example, our simulations are also on the order of 100 parsec, a couple hundred parsec resolution, and we do a 0.1 density threshold, and that works fine. If we went higher than that, we would be essentially artificially preventing star formation because we don't necessarily resolve gas once it gets super dense. We want to avoid making gas particles that are too dense for us to really trust the physics of it.
So I also think that it depends not only on star formation but also on the implementation of feedback. So if you have different thresholds for star formation, and if your feedback is very efficient and can expel the gas from the regions of star formation very efficiently, then you can get this self-regulation, and it also depends on resolution, and it depends on everything basically.
I agree to an extent, but I think that it is a really real limitation of each model, just given the resolution, the density at which you simply aren't resolving the multi-phase nature of the gas anymore. And beyond that, you then would have to have a star formation prescription that it takes that into account beyond that density threshold. Maybe there's different ways of doing that, but you do have a point where you can't trust the physics going on in the gas in your simulation.
I think Florent has been trying to get our attention.
Yeah, so to follow on this point, I think I agree that your recipe for basically any kind of physics, but in particular star formation, depends on the resolution that you reach, not in terms of scale, but in terms of physics. And the point is that the question that is written on the screen here is that gravitational instabilities of cell shading is just a matter of scale. Because if you reach the scale when you can resolve prestellar cores, so here we are talking in astronomical units, then the only thing that matters is gravitational instability. But if you want to consider the galactic or even cosmological context, you cannot reach this resolution yet. So you have to deal with what balances gravity, and that's turbulence. Because in the end, what matters for star formation is not what kind of gas it is, but how dense is the gas. And you get this via the balance between turbulence and gravity. So you have to take into account large-scale flows at galactic scale, the spiral arms, all this kind of stuff. And you have to put that in the context of turbulence. So if you cannot resolve cores or even molecular clouds or even substructuring galaxies like spiral arms, that's fine as soon as you understand that your star formation recipe, your subgrid recipe, has to be tailored to match the balance between gravity and turbulence in this environment somehow.
Well, I think we've addressed all these questions. Any other burning issues that people want to discuss? I wanted to ask C. Go and Radu Dragomir to come up to the front so we can thank them. So all of the speakers have appreciated that C has helped us make it possible for all the different laptops to very quickly connect. And Radu has been in charge of all the video recording and also turning the videos into little segments with appropriate title slides and putting them up on YouTube almost immediately after the presentations. Both of these guys are young astrophysicists who I hope will have very successful careers. So let's thank them. And Colin DeGraff and Avishai have done the organization of the talks into the various sessions and making sure that they're related talks together, and we couldn't possibly do this without them. And don't forget, if you haven't yet emailed your slides to Colin, it's colindegraff@gmail.com. Colin also has a memory stick with him, and he'll be glad to take them off your computer, or you can give them to him on your memory stick. Please do that right away. Most of the slides from the talks from the previous days are now up, although there are a few that aren't. You know who you are. So please do provide them. And it looks like Avishai wants to say something.
Yeah, I want to elaborate on acknowledging the contribution of Colin to the organization of the program. He did it almost independently with some ministerial guidance from me, but he really did all the work and solved all the problems, and I think we had a wonderful program at the end, covering many topics in a very sensible way. So many thanks to Colin. And of course to Joel, that took care of everything else.
Yeah, the local arrangement. But we couldn't have done it without you, so thanks also to everybody who came, all the good talks, and all the great discussions.